Good morning, afternoon, and evening, everybody. I'm Danielle McLean, Executive Director and Founder of High Sky Society. I'm so excited to introduce this month's distinguished speaker. But first, I want to tell you a little bit about High Sky. We exist because 10% of transportation emissions are from aviation, and that number is expected to triple by 2050. We believe that hydrogen is the only solution to decarbonize aviation. There are three big challenges with implementing hydrogen for aviation. I call them the big three: infrastructure, cost, and regulatory. We work with aircraft manufacturers, fuel cell developers, hydrogen producers, and everyone in between to help lower the cost and availability of hydrogen. And of course, we work with government, industry, and other organizations to help develop a safe path forward to regulate this nascent space. High Sky Society holds free monthly webinars on the third Monday of every month. That's what you're at right now. This is High Sky Monthly. Distinguished speakers include folks from Plug Power, Universal Hydrogen, High Point, Highmark, Plasma Kinetics, Luftcar, and so many more. I can't even put into words how much I've learned from these webinars. So thanks again for all of our distinguished speakers. Past webinars are available on our website, highsky.org/shop. And I really look forward to seeing what we're going to learn in 2023 throughout these invaluable webinars. And finally, our flagship event, Flying High, is June 21st through the 23rd. This is the world's largest hydrogen aviation event. We are so excited. We'll have over 1,000 attendees, over 100 presentations, and the network is just going to be unheard of. So whether you're an industry professional or just looking to learn more about hydrogen aviation, Flying High will definitely have something for you. Sponsors can showcase their services or products to over 1,000 highly targeted attendees, or you can join over 100 speakers to do a presentation on your service, idea, or company. We cannot wait to work with you. Tickets are available now on our website. Get them. This event will sell out. We have a limited number of sponsorships and speaker slots available, so I encourage you to get in now so that you can showcase your technology or company or idea to over 1,000 highly targeted hydrogen aviation industry folks. It's a virtual event, but not Zoom. I can't wait to see you at Flying High. So now let's jump into High Sky Monthly.
So I'm going to start and just say a few words about who we are and why we exist, and then I'll hand it off to JP to talk more specifically about the two technologies that we're creating, and then wrap it up in terms of the impact on the eVTOL sector and the kinds of performance models and some conceptual designs that we've created that I alluded to briefly out last time. But let me start with who we are and why we exist. So the company is called Universal Hydrogen. We are about a year old, just under a year old. And the company really comes out of both JP's and my experience in big aerospace. For my part, my last two roles were CTO at Airbus and then CTO at United Technologies, which is the parent of Pratt and Collins, and today part of Raytheon. And I've sort of been passionate about decarbonization and getting the industry set on a green agenda and on a course to meet the goals of the Paris Agreement for the better part of a decade now. And I tried very hard to do this from the inside of large companies, both OEMs, tier ones, propulsion companies, and it's hard, right? It's I think it comes as no surprise to anybody here that the industry is prone to kind of an incrementalist mindset. And while I think we were successful in making some of those increments a little bit larger, my big frustration as an aerospace engineer is that we are probably one of the largest sectors out there that has no credible path to meeting the goals of the Paris Agreement. And I frankly think that that's shameful, right? Because we're supposed to be on the bleeding edge of innovation. And my goal is to have people like Greta Thunberg, right? Young adults who are passionate about the environment, come work for the industry rather than be out on the streets protesting the industry. So universal hydrogen has its roots in the fact that JP and I came to the conclusion over the years that hydrogen is probably the only credible path to really decarbonize the industry at scale. And so the goal of the company is really just to make that happen, and to make that happen probably 10 to 15 years sooner. I think it's inevitable whether we existed or not, but I think that we can accelerate the adoption of hydrogen across all the segments of the aviation industry by a decade or more. And so we chose, the company is targeting principally the regional segment. And the reason we're targeting regional is because we think that it is a good entry point that is persuasive, that's a useful reference, both for aircraft that are bigger, meaning single aisle, right, which produces most of the emissions and flies most of the passenger miles in the aviation sector, as well as for everything smaller, which includes general aviation, and of course, most pertinently for today's conversation, eVTOL. But that's why you see a regional airplane, a Dash 8 in front of you. This is our vision for entry into service in 2025, which is the aim to be in certified passenger carrying service by 2025 in the regional sector. We can talk about where we could be in the eVTOL sector in terms of realistic entry into service, but I suspect the date wouldn't be too far from that 2025 target. And this image, there are two things. If you're a very keen observer of Bombardier Dash 8s or de Havilland Canada Dash 8s, you'll notice that the airplane has these radiators on the nacelle, which are there to cool the fuel cell and the electric motor. But that and the big hydrogen branded modules being loaded into the aircraft are really the only hints that this is a hydrogen aircraft. So it is a conversion, it is a retrofit conversion. And this aircraft has in the nacelle a fuel cell and an electric motor instead of the Pratt & Whitney Canada turboprop. And then of course, the other notable element is the hydrogen fuel modules, which is our approach to trying to solve the hydrogen distribution problem. So basically what the company's about is just making hydrogen work for aviation as quickly as possible. And in order to do that, we looked at the hydrogen value chain. And so along the top is the value chain for the hydrogen molecule. Along the bottom is the value chain of the hydrogen airplane itself. And there's been a tremendous amount of activity in hydrogen production. There's been a tremendous amount of activity in fuel cells. Right. So in both of those areas, we don't have anything new to contribute. We didn't feel like we needed to have anything new to contribute because we could just get that part of the value chain through partnerships. But actually getting the hydrogen from the point of production to the airport, to the airplane, to the aircraft operator is an unsolved problem. And doing that in a flexible way and doing it in a way that does not require incredible amounts of infrastructure investment into things like pipelines or fleets of tanker trucks, on airport storage reservoirs, tarmac fuel trucks, right, dedicated to hydrogen. All of that, if you add that up over the scale of the aviation system, even just the regional aviation system, adds up to very, very large numbers that globally would be in the trillions of dollars. And so that infrastructure is a barrier to entry. And so we try to solve that infrastructure through a clever approach. I think it's a clever approach, which is to move hydrogen across the intermodal shipping network, across the existing containerized freight network. And in order to do that, we created a capsule, which basically allows us to treat hydrogen as dry freight for purposes of transit, and then have that capsule be inserted directly into the aircraft and for it to become the primary fuel structure within the aircraft for the mission. And then we take the depleted capsules and do a reverse logistics chain on them. So that makes it compatible with the existing shipping network, which is itself represents an incredible CapEx investment that's already been made, has a lot of spare capacity, a lot of flexibility, and is probably one of the most efficient ways that we have as a civilization devised of moving stuff around the Earth. And then, of course, on the hydrogen aircraft value chain, again, as I said, in the fuel cell space, tremendous amount of progress and activity in recent years. So we are judicious partners in that space. And lots of demand from aircraft OEMs, and that includes eVTOL OEMs, as well as regional, as well as large commercial. But what is missing, right, is as most of you probably recognize, it's not just a matter of sticking a fuel cell into an airplane and saying, voila, I have a hydrogen airplane. It really requires integration as an entire powertrain, which requires a motor. It requires energy management, so a control system that sits on top of that fuel cell and motor, a thermal management system. Most fuel cells that are designed for terrestrial use have rather heavy thermal management systems. They weren't designed with weight optimization in mind, and they certainly weren't designed with certifiability, FAA certifiability or EASA certifiability in mind. And so we saw a gap in between the OEMs and the fuel cell makers. And so that's another place where we said, hey, there's a gap. The value chain doesn't work. We got to help complete the value chain by partnering on either end of the gap, and in the gap actually creating something new, which is a complete powertrain, a complete hydrogen powertrain for various classes of aircraft. Our first target, of course, as I said, is the regional market, which is about a 2 megawatt class powertrain for the de Havilland Dash 8 and for the ATR 72 aircraft. And then lots of operators, both cargo and passenger, that are very, very keen to decarbonize, that are facing increasing pressure from passengers, from flight shaming, from no-fly movements, as well as from governments to move on decarbonization. So, so long as the economics work, there's really no shortage of demand for adopting this. So this is really how our concept of operation looks for regional. It wouldn't be that different for eVTOL, except for the fact that, of course, you probably need much lower even cargo handling infrastructure in order to do eVTOL, right? Because the capsules are significantly smaller. The basic idea is we take hydrogen, so we sign offtake agreements. We have forward priced offtake agreements for many geographies today. We're adding more by the day. So we take green hydrogen offtake typically at renewable energy production sites is where it makes sense to run those electrolyzers. We fuel the modules. We put those modules in shipping containers. They go on trucks, they go on trains, they can go on ships, and they get to the airport. We do have two types of modules, and we'll only focus on one today, but we do have for the regional application, both high pressure gas at 850 bar and liquid modules that are form factor equivalent, and they present the same interface to the aircraft at the quick connect. So an airline can choose on a flight by flight basis whether they want to fly with liquid or with gas. Liquid is more expensive, but gets you slightly better range. Gas is cheaper, easier, has fewer logistical constraints on transportation. It can sit in these capsules almost indefinitely. So we're going to focus on gas as the primary approach that I think is most suitable for eVTOL, particularly with the fact that the infrastructure really has to be very, very flexible, right? With the number of conceivable vertipads where you would need to refuel the aircraft. So the modules go via intermodal freight, and then when they get to in this case, the regional airport, but in the case of an eVTOL, to the vertipad or to the vertiport, they can be handled using existing cargo handling equipment and infrastructure. So nothing new is needed. You don't need a storage reservoir. You don't need a hydrogen gas station. You don't need a hydrogen tanker truck or hydrogen fueling truck or anything like that. These modules are loaded like an espresso capsule into your coffee machine, and go directly into the aircraft. They can also be stored in a hangar or in a storage closet, right? If you really want. Once the modules are depleted, they're removed from the aircraft and they basically go into a reverse logistics chain, which is very similar to the forward logistics chain. Get inspected and get put back into operation. So that's the basic idea. And what JP is going to talk to you about here in a second is the specific module technology. Our gaseous modules are about twice lighter than a conventional Type 4 composite overwrap pressure vessel. And they are also designed from ground up, sort of on first principles for certification, for aviation certification. So that's the key difference between just buying what's in the back basically of a Toyota Mirai. And what we have developed here. Then the second thing that JP is going to talk about is the powertrain. So we are developing a 2 megawatt powertrain for the regional application. As stepping stones along the way, we will have a 100 kilowatt order powertrain and a 1 megawatt powertrain, which are pretty directly applicable to various eVTOL missions. And then the third thing we'll talk about is conceptually, what does a hydrogen powertrain do for eVTOL mission performance? And you'll see that we've used the Uber Elevate reference vehicle and reference mission and done a conceptual design of a hydrogen powertrain together actually with a battery. So it's a hybrid hydrogen fuel cell battery type application. And that yields incredible savings in weight volume. So with that, just maybe a very quick introduction on JP and a little bit on the rest of the team. So JP is our CTO. He's on the faculty at UT Austin. Before that, he was at Georgia Tech, and before that, he was at MIT. As a faculty member 20 years ago at MIT, actually, he was my senior thesis advisor. So we worked together for many, many years. Also a serial entrepreneur and spent some time in industry, both at United Technologies and before that at Boeing and before that at NASA JPL. We have a very strong executive team. Rod Williams, who's our chief commercial officer, is also on the call here. He's a longtime Bombardier executive where he ran regional programs as well as marketing, and then was an executive at Wheels Up. And then we have also a strategic advisory board, which includes some very notable characters, and they're there not just because we like to hang out with cool people, but they're really there to de-risk a lot of the facets of what we're trying to do and trying to do very quickly. And that includes things like certification. So we have a very aggressive path on certification, and really trying to get the FAA to move on this quickly, noting that certainly the fuel cells and electric motors are not issues of first impression for either the FAA or EASA, but putting them together into a powertrain and having this new approach to storage onboard on-aircraft storage technology are new things. And so there is plenty of certification work to be done there. And so that's the advisory board is really there to mitigate that risk and as well as commercial risk for us. So with that, JP, would you like to take over and talk about storage?
Sure, no problem. So as Paul mentioned, the two things that we're working on, one is a storage system and the other is a powertrain. I'm going to talk a little bit about the gaseous storage system first and then about the powertrain. Next slide, please, Paul. And as Paul mentioned, I'm a faculty member, so you got to have like a theory slide somewhere around the place to explain what our underlying philosophy. So we are on the aerospace industry. We know that we have very stringent weight, volume, and safety requirements. And so one of the things that when we looked at the problem was we looked at the type 4 carbon fiber overwrap pressure vessels, and we realized that with that weight, we couldn't make the case close. Basically, we couldn't make the system design case close. So we took a step back and we thought very hard, and we said, let's apply the principles of axiomatic design. And for those you don't know, this was an idea that NAMSU put forward in the 90s, late 80s and early 90s, of how you actually go about taking things from customer needs to functional requirements to design parameters to process variables. And so the idea is how you flow down the requirements. And what NAM basically pointed out was if you can keep the functional requirements independent, right? That's each one is like a basis vector. And you can actually then keep the information content low, which meant that you didn't have to trade off a lot of things between different functional requirements in the design parameters. You could get a really, really well optimized system. So the idea here is that for us, we need to contain the hydrogen. You need H2 impermeability. You need to contain the pressure loads because in order to get at least the regional turboprop case to close, we need to get the 850 bar. You need to be worried about abrasion and impactor loads, and you need to worry about crash loads. Now, if you think about that, if you're trying to build one sort of hemispherical ended capsule / tank to meet all those, you get a really, really heavy thing. So what we did was said, okay, let's then, using this principle where we want every function to be satisfied by one design parameter, how do we contain hydrogen best? So we looked around at the technology and we said, we could come up with, we can use, and they exist, barrier membranes that are very light, very thin, that just contain hydrogen. Obviously, they can't contain a lot of pressure. However, if we use carbon fiber by itself without a lot of pre-preg, we can lose the weight of the pre-preg and we can create a carbon fiber weave that basically sits outside this, this membrane, and there'll be multiple layers of the weave, and that will hold the pressure. And then if we then put another layer outside of that with the Kevlar or some similar aramide, we could actually then deal with the abrasion resistance. And then finally, if we put all these in a truss, which we all know from our introductory course in structures is the best way to carry these loads, we can deal with the crash loads through a frame that sits outside that. So ideally, basically, we have all our functions being satisfied. Each of these functions are being satisfied by a specific design parameter, physical instantiation, which we can certify against that one functional requirement with minimum interaction between these, which we propose will help in terms of getting this certified as well. So with that principle in mind, we ended up, next slide, with a system that looks like this. And this is actually, these are, the pictures in the bottom left are actually real pictures of our subscale model that we have built and started testing. So
and I can hold it up while you're talking,
yes,
JP.
and Paul likes to hold it up. He's going to be Vanna White for a second there.
I'll bring it. I'll get it.
Okay, all right. So anyway, so you can see here the membrane in the very far bottom left, the membrane that keeps the hydrogen in, and then outside we have actually, this is a carbon fiber weave, and then both of the membrane and the weave, and then this yellow is the Kevlar on the outside, are all mated in a boss that we specially designed to actually hold and transfer the loads into the boss itself. And so this is the one that Paul will bring is kind of on the size that you'd actually probably going to end up thinking about for eVTOL from the smaller eVTOLs. And then the picture on the bottom right is the one, the colorized one, because I think we like deep blue purples, on ours. That wasn't my decision, by the way. On inside the frame, and then Paul can hold up the subscale model right there for you guys. So when it was all done, and we actually ended up with about, in the whole thing with the frame, about 17% mass fraction. So of the entire system fully loaded, the storage, 17% in hydrogen, which is about twice what you could get, what's the best in class for composite carbon fiber overwrap pressure vessels. And so that really was very nice for us. We're actually in the process of building a full-scale model right now, and with plans to start testing in the April timeframe as well. So the next thing that we had to tackle was the powertrain. As Paul said, getting to the right magnitude of power was tough because it don't really exist. So we again did some good design principles. So this is the Dash 8 nacelle here showing you what it looks like sitting in that nacelle. Obviously, the Dash 8 has a pretty generous nacelle, so that was a plus. Our design constraint was to use the existing propeller, no change. Use the existing nacelle as much as possible, and we had a design constraint to minimize changes to the outer mold line. So what we have here is that we're going to be bringing the hydrogen in through the wing from where to be stored inside the rear of the fuselage or wherever it would be in a you decide to put it, and then that would come in straight into the fuel cells, and they would sit behind the motors and the motor controllers and inverters. And then we'd have a zero drag radiator, and this was inspired by the P-51 Mustang, which is basically to have a shaped cowling around the radiator so that you can actually, because you're introducing energy and the exit area is smaller, you generate a little bit of thrust or just enough thrust to counteract the actual added drag for the radiator cross section and as well. And so we also have here the batteries, because you need to, even though you have the fuel cell being the primary driver, you need the batteries for surge and for situations where you have need for very high power requirements. Fuel cells are really great in terms of specific energy, as we know. But when you need to draw a lot of power, you have to have a lot of fuel cells stacked up. And so that was one of the reasons why we have the battery here to deal with transients. But in the eVTOL case, which I'll talk a little bit more in a second, we were definitely need to have a greater amount of, slightly more batteries, but because you wanted to have the high power, specific power. The other thing I wanted to point out in our powertrain is that one, as Paul mentioned, the compressors in the existing fuel cell systems for terrestrial are not really optimized for weight. And so we're in the aerospace business, we know how to do that. And so we are actually designing a first and second stage compressor and a turbine, where the second stage and the turbine are linked, like as they would, and then the first stage is actually driven by a motor. It could be tapped off the primary motor, or it could be have a peripheral motor. And we have both architectures depending on the specific requirements of the vehicle. But the key thing I want you to take away from this slide is that our system, because we have control at a very high level of the motor controller, we have the fuel cell controller, we have control of the flow rate from the hydrogen, and we have control of the first stage compressor, independent of what's happening inside the fuel cells. We can then do very clever timing of spooling up and spool downs, which give us very, very, very good aggressive spool up times. And we actually like to think that our vehicle is going to operate like a Tesla or another eVTOL. I mean e-car in terms of takeoff, acceleration, and climb performance. In fact, the lapse rate on these engines, these powertrains, are actually less than they are in a conventional engine. And so we'll expect to have better climb performance as well. Next slide, please. So as we were going through and we're thinking about getting there, we realized that since we're building a initial sub 60 to 100 kilowatt powertrain, and then a 1 megawatt powertrain and a 2 megawatt powertrain, we quickly realized that the 60 kilowatt powertrain, which will be running actually probably week after next. And so if after the pandemic is over, if anybody wants to come to LA and check out a running 60 kilowatt powertrain, please let us know. So anyway, so we realized that it would be good to apply this to eVTOLs. And this is what we're going to basically talk about. I'm going to talk about for the rest of the time. We looked at the Uber Elevate reference design because that was out there in the public. And as you can see, for that design, you have a payload about 450 kilograms, empty mass fraction about 57%, LOD of 14. And some of the numbers here, we actually then inferred based on the other numbers, but we have, as a consultant and a part of our team, Brian German from Georgia Tech, who is very well versed in eVTOL sector. And so we use the numbers, the vehicle and the mission requirements. We also then size the hover power for the sort of an emergency out case, which is a 5,000 density altitude, one motor out, 500 feet per minute vertical velocity. And we assumed, of course, it would be a tilt rotor, tilt wing with 4 passengers and luggage. So these were our mission requirements. We went through and we said we could satisfy those mission requirements in one of 3 ways. One, we could use a high specific energy battery, which is sort of the de facto or baseline way of going about it, with about 300 watt hours per kilogram, a C rating of 10, basically a packing energy density of about 150 watt hours per liter. Or we could use a fuel cell and gaseous storage system, a GH2 storage system, which together gave you much greater specific power. However, the gaseous density is the whole density of the system, it goes down. There's also another way, which is to basically do a hybrid, which is where we end up looking at, and we're going to compare this, where you take a high specific power battery for the hover and takeoff components, and then you use the fuel cell for the cruise component, and also to recharge the battery. And so what that gives you is the fact that batteries, especially the high C batteries, are really good in terms of giving you the power you need with relatively low mass and low volume. And then you can use a fuel cell where it is really best, which is it's really good at high specific energy. And so we did this analysis with a mission where we assumed batteries stay between 10 and 90% for preserving health, where they degraded to about 80% of capacity at the end of life relative to the beginning of life. And we also used about 10,000 hours at the end of life for our fuel cell system with the appropriate degradation over time. And we did this with our partners, all this work at Plug Power. Next slide, Paul. So when we were all done and said, we ended up with the following. So for our battery system, 450 kilograms payload, we ended up for a battery, the system would weigh about 3,200 kilograms. And the actual volume of battery required would be about 900 liters of volume of batteries. Now, if we did just a straight fuel cell system, it would be heavier and it would require more volume for the fuel cell and hydrogen storage as well. However, if you, again, compartmentalize, and again, this is almost a recap of the axiomatic design, which is you need to have the function for vertical takeoff, and you need the function for cruise. If you can then separate them and have each design parameter meet the optimally, we end up with a system which is about close to half the weight of the battery system, your baseline system, 1,700 kilograms. And because of our storage technology, it turns out the volume required is actually about 350 liters, which is very small compared. It's basically less than half what you would have needed if you had the batteries. So this hybrid solution looks really, really good. 2 times lighter, more than 2 times smaller in terms of the volume, which gives you more carrying capacity. So it opens up a great deal of potential. And when you're going back to the basics, you see why it makes sense in this graph. And Paul especially loves this graph. He calls it the magic graph, but which shows how aircraft weight, the vehicle weight, would change the function of range. And what you see there is relatively straightforward, right? So if you had the battery by itself, as you increase the range, your battery weight quickly builds up, because once you deplete the battery, there's no, it doesn't have the kind of specific energy that you need, so that the weight just starts to grow. Now, if you had a fuel cell system, on the other hand, you're going to start with a heavier weight because you have to buy all that fuel cell weight onto the aircraft. But then once you get that bought on, the added hydrogen you need to go more range is actually it's very low. So your slope of your line as you increase in range is pretty low. Now, the one in the blue is our hybrid solution. And what you see there is that you just get enough batteries to deal with your vertical takeoff, and then you get just enough fuel cells to deal with your cruise. And then your added range is just given by the weight of the hydrogen, and the weight of the hydrogen is not that big a deal in the big scheme of things. And another way to look at it is basically look at the energy. The next slide there, Paul. You got it? Is to look at the specific energy versus range. And you can see quite clearly here that the battery has a constant, specific energy. But as you basically increase range, you get more and more specific energy because of the hydrogen. The added cost in terms of the hydrogen, in terms of weight, basically is just marginal as you go along. So I will stop there, and I guess we should go into Q&As, right? Right, Mike?
Yeah, thank you, guys. That was great. A few questions have been posted in the chat room. I'd like to just quickly review those, which I've now done. So I'd like then to open the floor. And since we have about 50 people on, if you could, there's a function called, where is it here?
Raise hand.
Raise hand. Yeah, do that, and I'll see if I can. Mind you, I can only see about a third of you at a time. So let's see. All right, raise your hand again.
Maybe we can take the ones in the chat first, Mike.
Fine, let's do that.
Yep.
Then I'll try to figure out how to see you. Okay. So Amanda Simpson, questions. When installed on a multi-engine aircraft, do you plan for power sharing in the case of partial failure?
Well, on the case of the regional turboprop, we have each nacelle would be able to carry all the power on that side, and so it would carry full power on that side. So we do have crossover for the hydrogen leads, but we don't have actual electricity crossover from one fuel cell to the other, one powertrain to the other, because we're treating them as if they would be independent systems for right now. However, there is a possibility that's going to add added weight. So right now we're just basically saying we'll have crossover leads of the hydrogen, like how you'd have crossover leads of fuel flow, and we'll treat each nacelle in the regional turboprop as being its own independent powertrain. But there is potential for crossover of power, and that's something that we can add. It would be an added safety benefit.
Very good. This was from Elijah Shoemaker. How long is the transport chain from tank fueling to airport? And how do you manage the boil-off hydrogen in your LH2 transport tanks during distribution?
Okay,
so we have designed, why don't I take this one, JP, just to give you a break. So we've designed this for, what I presented early on, right, was a regional application. And so typical regional network is going to be, between the hub and the end nodes somewhere in the high hundreds of kilometers, right? So let's say between 500 and 1,000 kilometers. So we designed that, we assume that there is a green hydrogen offtake point somewhere within the span of that regional network. And so we've been looking and establishing those hydrogen offtake agreements on an airline by airline basis. With renewable energy suppliers and electrolyzer operators within that footprint. So typical transport distance would be between 500 and 1,000 kilometers. And one of the unique things, we focused obviously on the GH2, right, the high pressure gas design here, because that's more pertinent to the eVTOL mission. For the liquid design, we have a different capsule technology. It is two-wall metallic. It's a two-wall metallic cylinder with some unique insulation properties. But one of the other unique things about our design is it's actually also a pressure vessel. So we can confine the boil off. So we don't vent the boil off for up to 40 hours. And that allows us about a day's worth of transport by truck, right, to get from the point of production to the airport. And then about a day's worth of storage on airport before you either have to start consuming from the tank or you actually have to do a safety vent in order to get rid of the excess pressure.
Very good. What are the safety issues? This is from Tom Freund. What are the safety issues? What are the safety issues with module transportation, storage, and probably especially onboard use?
So let me maybe answer high level, and then JP, if you want to elaborate in more depth, please. So there are two different sort of safety and regulatory regimes associated with terrestrial transportation. In the US, the Terrestrial Transport Authority, Safety Authority, is called PHMSA, Pipeline and Hazardous Materials Safety Administration. And they have a certification regime for on-road. And I think PHMSA also, together with the rail agencies, covers rail transport. Maritime is a third thing. But for truck safety, PHMSA has a regulatory regime. They are a different agency in kind from the FAA, so they have a much more empirical approach where you have to pass a certain set of tests, but they don't insist on understanding all of the failure modes, for instance, in an analytical way, the same way that the aviation certification regimes do. And then separately, of course, we have the aviation certification regime, right? So we design for a combustible pressure vessel on board an aircraft, right, with all of the safety factors and all of the different hazards analyses that come along with that. And so, JP, I don't know if you want to give an example or two of what those are.
Well, the way I like to think about PIMSA is PIMSA has a very rigorous set of tests that you have to pass, and you can also have waivers where you can mitigate the need for certain passive system requirements by using active monitoring. And so we have basically looked at all of those, and their requirements in some ways are more stringent than aerospace, because if we don't have their level of safeties can be a little bit higher than ours. But you can find a compromise there by actually optimizing with your monitoring and PHM systems to actually get the solution that closes. So we have done that. We have designed to the aerospace standards, and where necessary, we have also designed monitoring and mitigation systems for the storage of the system and the transportation on the ground.
Very good, very good. Thank you. This from Bruce Holmes. Can you say a little bit about the fuel cell stack cooling requirements and whether the water capture can play some kind of role?
Yes. So the cooling requirements are indeed very high. And you're right, Bruce, in that the water can play a role, and does play a role. We have, as part of our technology, the ability to actively manage how much heat gets deposited in the water that gets stored, and when to dissipate that water, so that to avoid the generation of contrails. And that's part of our solution, that we didn't want to create one problem by solving another one. And so, yes, it does play a role, and we do have the ability to store the heat in the water for a short time intervals whenever we have like surges in power, et cetera, and things like that.
Very good, thank you. One more question here from Paul Stith. With regard to swapping modules, what requirements will you have for ground crew certification in order to do things like replenish fuel, safeguard the supply chain in some type of certified framework, I guess?
Right. So with regards to actually loading it on the airplane, we are doing our level best to make it as simple as possible. So in terms of the modules, they would be all self-contained. They would be loaded in using existing cargo loaders and onto ball mats or equivalent rails, and locked in using existing cargo handling, cargo locking mechanisms. Obviously, we're going to have to make the connect, and so we'll be using, in as much as possible, standard certified quick connect capabilities. And that's one of the reasons why we're trying we don't have any refilling being done or anything like that at the airport. It's really just moving these modules around, or at the vertiport, moving the modules around, putting them in, locking them in place, and doing a quick connect and closing the door. So we expect, we don't know, we're hoping that there will be minimum levels of additional certification required in terms of loading this in the airplane. In terms of monitoring the supply chain, we have spec'd out and designed a very extensive monitoring scheme for loads and for and changes to the actual physical infrastructure, as well as software from beginning to end. So the place where we would actually have to then get certified would be on the filling locations, which would be, much smaller in terms of number, much fewer in terms of number, and where we would have folks in our organization or trusted partners doing the filling, and that would require, then we would deal with the certification around that end.
Very good. This next question is from Daryl Swanson. What is the expected payload and range of that de Havilland aircraft you showed on chart 1?
Okay, so we have a module we have a 3-module solution for that Q300, or sorry, the 300, because they don't like Qs, use the word Q anymore. The 300, -8 300. And we can use either 3 gaseous modules, and that can give us a range of up to about 400 nautical miles with 40 passengers, or 41 passengers, sorry. And then, or if you want to get up to about 550, 570, you could get that with 3 of the liquid modules. We have designed the modules to be form factor consistent between liquid and gas. So depending on your specific range of the specific distance you're going to fly on a particular mission, you can swap out gas versus liquid for each of those. And the liquid obviously will bring everything down, so that the connection, that quick connect to the aircraft would be the same in terms of pressure, et cetera, for the liquid as it is for the gas.
And as a follow-up to that, what are you looking at with respect to operating costs?
So the operating costs, one thing also to point out, right, is that those modules in the back of the aircraft, they take the place of 2 rows of seats. So there's basically a loss of eight seats. And so when you look at operating economics, if you look in terms of cost per available seat mile or cost per available seat kilometer, you have to take into account the loss of those seats. There are some countervailing factors, like the fact that a hydrogen powertrain is actually end-to-end more efficient, right? Because you're not limited by thermodynamic cycle efficiency, like you have no Carnot efficiency limit, right, on electrochemical energy conversion. So you get about a 10% bump in the end-to-end efficiency. You also get a pretty significant bump in maintenance costs, right? Because the fuel cell has no moving parts. It's a stable thermal environment. So the maintenance and overhaul footprint for a fuel cell is much less expensive than it is for a turboprop motor, turboprop engine. So those are kind of the countervailing non-fuel factors. And then in terms of the cost of fuel itself, so you get rough equivalence between hydrogen and jet fuel at $3 per kilogram for the cost of green hydrogen. And today, green hydrogen you can get maybe between $5 and $6 per kilogram, depending on the region. Of course, the principal driver of that is the cost of input renewable electricity, which varies pretty widely. But if you pick Seattle or something, right, where you have the Grand Coulee Dam, right, you can get 4 cents per kilowatt hour hydropower today, right, which gets you into the $4 or $5 range on the cost of green hydrogen output from an electrolyzer. So the $3 per kilogram we think is broadly attainable around in most places in the world by 2025, which happens to be our entry into service date. So we expect to be able to offer basically equivalent CASM in the regional application by 2025. And then the cost of green hydrogen looks like it's going to follow, the equivalent of Moore's or Swanson's law, right? I guess is the PV photovoltaic version of Moore's law. It looks like green hydrogen is on a similar sort of trajectory. So we now have offtake agreements. For instance, we have one for Canada that gets us down to $1 to $1.50 per kilogram by 2030 for green hydrogen. And that's not projected, right? That's a real commercial forward priced agreement with a vendor. So the operating economics get drastically better, equivalent 2025, and get drastically better in the years after that because of the drop in the cost of hydrogen. We have not done operating economics for eVTOL, I should point out, right? So this is a baseline comparison based on the Q300 airframe.
Very good, thank you. A question from Amanda Simpson again. For eVTOL with distributed lift units, have you evaluated complete powertrains at each propeller or several decentralized fuel cells? What's the working concept here?
Well, right now we have actually just assumed that we'll have smaller powertrains, but we can do the thing is that you have to then worry about the shielding for the electrical cables to carry the power, which depending on the voltages can have issues. So we haven't fully fleshed that out yet. We have assumed that it would be separate powertrains for each one, because what we found in the in the regional turboprop, it was easier to plumb the hydrogen than it was to plumb the electricity in the end.
Very good, thank you. Okay, so we're going to do a little experiment here. Since I can't see who's putting their hand up easily, I'm going to allow everybody who wants to have a question to take yourself off mute, and let's just see if this works.
Oh, wow.
And who would like to start? Bruce, you always have questions.
I do. Yes, I do. First of all, JP, great to see you. It's been too long, my friend.
That's right. We should get together and chat. So
I think so. So the forecast for total cost of ownership of hydrogen fuel cell powertrain systems by the DOE is promising. Have you looked at pricing those changes, those trends into how it might affect seat mile fares, for example, maybe even just very roughly by percentage?
Yeah, we actually have CASMs worked out, cost per available seat mile. And as Paul was saying, that by 2025, we are probably around, depending on the cost of electricity, obviously, because that's really the big thing, if you're in Europe or in the US or Canada or wherever. But in the most promising sectors, I think we're probably about 90% lower. I mean, not 10% lower, 90% of what the CASM would be. And that will get better over time. So, so it actually works out really well from an operator perspective in terms of operating these vehicles.
Sure.
Bruce, maybe one comment I would make on that, right, is like we try not to rely on either for the cost of hydrogen or for the maintenance cost of fuel cells or the procurement cost of fuel cells on like aggregate, DOE style parametrics. We rely on very specific commercial agreements because we got to deliver to them, right? So that's why I went out of my way to point out that our cost of hydrogen is based on real forward priced offtake agreements. The cost of fuel cells is based on Plug Power's actual supply cost to us, right, of those fuel cells. And the maintenance intervals are based on the many millions of hours that they have in their fuel cell fleet terrestrially. And yeah.
Nicely done. Not your first rodeo. So.
If I can just intervene, Rex Alexander, I think you're listening. And for those of you who don't know Rex, he's one of the country's foremost helipad design and construction experts, and just finished a standard, which maybe you can talk a little bit about, Rex. And of course, my question for you is how would hydrogen fit in if perhaps we are going and coming from a rooftop somewhere?
No, thank you, Michael. Great to see all the great people attending this today. Yeah, as far as the standard goes, there's a couple different standards out there that are in the mix. One is the one that is for vertiports is ASTM vertiport standards. That is primarily centered around the geometry of the vertiport and the airspace. I think the one that Michael's talking about is this one that just was published is National Fire Protection Association 418 standard for heliports. In this, just was published January, we actually define the term vertiport and vertistop, but we also put in a new chapter 11, that outlines vertiport structure. And in there, we actually have attached a reserve section specifically for hydrogen storage, hydrogen refill, and things like that at vertiports, be that at an airport, ground level, or rooftop. So we'll be starting that process of vetting that and putting information out over the next 3 years, probably this summer.
Yeah,
so,
and we would be delighted to help provide info.
No, and I'd be more than delighted to get you involved. Now, in the space, I represent the Vertical Flight Society on that committee for NFPA 418. So as time goes on, probably April, May, you should probably see something being published in Vertical Flight Society looking for people to
Okay.
participate. The good thing in the hydrogen side of the world is the National Fire Protection Association has a tremendous amount on the books already that speaks to hydrogen. If you haven't looked, you can go to NFPA website, look at NFPA 2. There's a lot there already. We just need to take it and bring it into the aviation world. So, but
yeah, we've been looking at that in terms of placement of stuff for obviously powertrain and storage.
we're trying to bring the Vertical Flight Society and the NFPA together in one big happy family. So anybody interested, don't hesitate, let me know. Thanks, Michael.
Very good. Very good. Who's next? Bud, go ahead.
This is to thank Paul. You have brought us halfway to our goal, so a great accomplishment. I very much like what you're doing. Would you please make a comment about your mass fraction for your liquid hydrogen double-walled tank? As I understand, you said double-walled, but it is also under pressure. So pressure plus cold sounds like a halfway, that seems to be a much more powerful way. But what's the mass fraction, if in fact you guessed that one already?
No, we didn't guess. We actually have it computed. So the mass fraction with the two capsules, we call them, in this case tanks for the liquid, plus the frame and everything and the manifolds is about 28%.
For liquid.
For the liquid, 17% for the, so if 17% for the gas, 28% for the liquid.
I wish I met Paul 10 years ago. When you were at DARPA, I tried to wrangle money out of DARPA about 10 years ago. So, and you were off to flying 100 years of a spacecraft that's going to go 100 years out to another space. That's you, Paul. Thank you. Not that I want to go there. But
Very good.
Yes, sir.
Very good. Very good. Very good. So who is next? We have room for a couple more questions. Then we have other business. I can't see you, Amanda. I can see Amanda.
Sure. Hi. And good to see you, Paul. JP, thanks for participating. A quick question. I put it in the chat, but with a 40-hour limit on the tanks, that's kind of going to be challenging even to eVTOLs, which are thinking of, just plugging in and recharging and thus having unlimited access. Having only a 40-hour window to transport and use, what would it take to increase that storage time or understand how much has been lost so that you can compensate your range accordingly?
Right. So
I just want to make sure. Yeah, I just want to make sure that we clarify one thing: is we're actually not proposing the liquid hydrogen solution for eVTOL.
Right. No.
We're proposing the gaseous hydrogen solution, which has no dwell time constraint. Right.
Oh,
it can be stored indefinitely. Right. Now, So the reason we're even doing liquid is it gets you, an additional increment of range in regional, where range is the issue, right? And then it's also a path towards single aisle, right? Because again, our mission here is to decarbonize all the different segments of aviation, at least as many as we can. So that's why we even brought liquid into the discussion, but don't want to confuse it, right? And so the proffered solution that I think works for the vast majority of eVTOL applications is going to be the 850 bar, maybe even lower. We may be able to get away with lower pressure for gaseous hydrogen, and then there's no logistics, there's no dwell time, there's no storage time constraint.
Thank you, Paul. You have clarified my confusion.
All right, one more question.
Hey, Michael, this is Steve Hanby.
Yeah, hi, Steve.
Yeah, hi. Thanks, Paul and JP. That was a great, very enjoyable. How did you treat with Plug, as just the example that you're using, the balance of plant in terms of your mass fractions?
I see Thomas Jones is on the call, so he'll start smiling or scowling if I say anything else. So we basically did a component-based look at it, where we basically said we want the stacks, we will deal with the cooling, we will deal with the compression, we will do everything. So the balance of plant was basically done by optimizing both the motor cooling, the fuel cell cooling, all the power you need for hydraulics, cabin, everything. So we designed the whole powertrain, assuming that the fuel cell was just supplying just the stack itself, and we did the entire thing optimized, which, as you well know, that's the way to actually achieve the kind of savings in terms of both weight and volume that you need.
Perfect.
But at the same time, to get the cost structure of the fact that Plug Power is the preeminent producer of fuel cells, right? And they can get volume and scale effects, which help the economics drastically on the MIAs, right? The membrane and electrode assembly, right? And the core of the fuel cell stack. So we're kind of wanted to have our cake and eat it too. So we're each doing what we think we're best at. Plug Power doing very high performance, very low cost stacks at scale. And us doing the aerospace specific applications and the certification.